Okay, after the other class leaves, you're welcome to come in. You don't have to wait outside. Normally that door is unlocked, so just pull it. You should be able to get in. Were there any questions? Okay, we're going to continue chapter 5 stuff, and then I'll talk about the exam later. But yesterday we left off with metathesis. Metathesis are basically just your double replacement reactions. You know, the only difference is I don't call it double replacement, because if I call it double replacement, then certain things confuse people. So let's say you had something like this. Let's say you had magnesium nitrate, and you got to make sure you know your nomenclature, because for exam 2, I'm going to give you the name. You have to write the formula. If you get the formula wrong, then you lose a lot of points. And so by exam 2, you definitely have to have your nomenclature down. Otherwise, significant points lost. Aqueous ammonia. This is aqueous magnesium nitrate, but even if it's solid, if this were solid magnesium nitrate and you put it into an aqueous ammonia solution, that solid magnesium nitrate will dissolve. And so, do that. It's a soluble strong electrolyte. All nitrate salts are soluble. But what if I did this? What if I put in some sodium chloride? Something like that. Or what if I put in some potassium phosphate? What would you do? See, this doesn't fit the AB plus CD pattern, and so I call it metathesis because all we're looking for are favorable ion combinations. So you look for all the favorable ion combinations that we have here. Now, I looked, and a lot of people had this right. What do you do with aqueous ammonia in metathesis? Add H2O. And when we add H2O, what happens? We form, a little bit of ammonium and a little bit of hydroxide. So the reason I call this metathesis is because magnesium nitrate is going to be magnesium ions and nitrate ions, sodium ions, chloride ions, potassium ions, and phosphate ions. And then we look for all the favorable ion combinations. So for example, hydroxide and magnesium like each other, and phosphate and magnesium like each other. So in this particular reaction, I'd expect two precipitates, a precipitated magnesium hydroxide and precipitated magnesium phosphate. And so not all reactions fit in the simple AB plus CD pattern. And so this makes it more complicated because I'd expect a mix of products here. Does that make sense? And so oftentimes I'll throw in, everybody's used to the AB plus CD, but if I throw on an EF, then a lot of people leave it blank. All of a sudden it doesn't fit their expectation and throws people off. But it shouldn't throw people off, And so a metathesis is just trying to exchange all the ions and see if you get a good combination or not. Okay. All right. We're going to move on here. Yeah, I'll give you those back to you. The metathesis equations from yesterday. The next type of reaction that we look at are acid-base reactions. And we have Arrhenius. These differ by the definition. The Lewis is all-encompassing. And so if I think about the Lewis, everything is Lewis. But a small subset of these would be Arrhenius. And so And a larger subset of these would be Bronsted-Lowry. But if we analyze everything with Lewis, it's more difficult. In other words, Lewis is the broadest definition. It encompasses all acids and bases. Bronsted-Lowry is a narrower definition. Therefore, some acids, actually a lot of acids and a lot of bases are left out. But the analysis is a lot easier, and a lot of the acids and bases that we deal with are Bronsted acids. And so this is just easier. Arrhenius is just H plus is an acid, OH minus is a base formed from water. That's Arrhenius. Where did I go here? Bronsted acids and bases are a proton donor and proton acceptor. And so we just look at the H plus, you know. Lewis's electron pair acceptor is the acid. And the base is electron pair donor. This is the acid. This is the base. Proton donor is the acid. In Bronsted, proton acceptor is the base. So if you want to know Arrhenius, this is it. That's all. So let's look at Bronsted. Bronsted-Lowry acid-base reactions. The goal here is, what we're going to do is we're just going to transfer one proton. There's overlap here because we have metathesis style Bronsted-Lowry acid-base reactions. And so we're going to treat these two differently. I'll talk about that here. So even though it could be consecutive reactions, there could be multiple steps, we're just going to do one step at a time. And so let's say an acid is triprotic. We only transfer one of the three protons. If it's diprotic, we only transfer one of the two. Now, what happens with the remaining protons? The remaining protons can react in subsequent steps, but we don't deal with subsequent steps yet. We have to finish the first step. And so this is why I say transfer only one proton, even though there could be multiple protons. From the acid to the base, and then determine if further, determine driving force, and then determine if further reaction occurs. That is, if there are additional protons that could react. We'll look at those. But for us, this determining consecutive steps, we're going to, most of the time, not look at that. We're just going to look at the first step. So the method that we use for this is we inventory. What I mean by inventory is you determine the major species in solution. The major species in solution are going to be determined based on its solubility and electrolyte properties. If it's insoluble, the major species is like the solid or liquid. If it's soluble, then the major species depends on if it's a strong electrolyte. If it's a strong electrolyte, the major species are the ions. If it's a weak electrolyte or non-electrolyte, the major species are the molecules. Leave them together. To determine the strongest acid and the strongest base present, we consult the chart here. And so all we do is we look at the acid-base chart and then determine what we have. And then we transfer a single H plus from the acid to the base, and then determine driving force, and repeat if necessary. So the first example is phosphoric acid. What's the formula for phosphoric acid? H3PO4, good. And sodium hydroxide? NaOH. So the step is inventory first. Okay, both of these are aqueous. So I'll just emphasize that by writing the states here. Is phosphoric acid a strong acid? Is it one of the 7 common strong acids? No. Therefore, it's a weak acid. Weak acids, do we ionize? Weak acids only partially ionize. If they only partially ionize, the major species present is H3PO4 molecules. Sodium hydroxide we consider a, well, it's the hydroxide that's a strong base. We consider it a sodium salt. Sodium salts are all soluble, and soluble salts are strong electrolytes, so we're going to have sodium ions and hydroxide ions. Then hydroxide itself can hydrolyze water, but it just makes it salt. Okay, there's one other species present. What is the one other species present? Water. Water is a solvent, but water can react in acid-base reactions, so we have to consider water too. It's aqueous. All right, then what we do is we consult the chart. So let's take a look at the redox chart. The redox chart, I think I forgot to save this here yesterday, so maybe it didn't post. Redox chart, I put it week 5. Oh, shoot. This redox chart I wrote all over. I need to post a clean version of the redox chart. But that's okay. We're going to use that chart right there. Do you see that? This is the acid-base chart. I'm just going to use that. What's that? Or let me just get one off the internet. All right, then we look at the, although this is hard to see. Let's see if I have a better example. This one from ResearchGate. Okay, this is better. This is, our chart has more entries. This is a little, resolution is pretty poor, but we have the strong acids here, HCl, H2SO4, HNO3. All the strong acids are treated as what? Equals. Due to what effect?
Plateau.
It's not called the plateau effect. It's called the leveling effect. So we look for everything that we have present. And so we have phosphoric acid present, that's an acid. And then what else is present? in our inventory. So let's take a look at the inventory again. We have sodium ions present. So what I do here is I look at phosphoric acid. Phosphoric acid occurs on the left side are the acids, the right side are the bases. But here I have dihydrogen phosphate. Do I have phosphoric acid on the right side too? When I look at the right side, there's no phosphoric acid on the right side. So the only thing that phosphoric acid can act as is an acid. And so below phosphoric acid, I'm going to put an A for acid. And then I look for sodium ions, but I don't find sodium ions on my chart. Now sodium ions, then I think, are sodium ions a good H hydrogen donor? There's no hydrogen atoms in sodium, right? And it doesn't want any hydrogen ions, H plus, because positive and positive usually repel each other. And so what I'm going to do is I'm going to put N for neutral. Or not applicable. Then I look at hydroxide. So I'll go down on the left side. So I see hydroxide on the acid side. But take a look. Is hydroxide a very good acid? No, but it still can donate a proton. If it donates a proton, it forms this. This is called a conjugate pair. So if hydroxide donates an H+, we're left with oxide. Oxide is the conjugate base of hydroxide. What's that? So hydroxide is an acid, but it's not a very good acid, but nonetheless, I'm going to write A here. You know what hydroxide is? Hydroxide is a much better base. In fact, it's a strong base. It's the strongest base that can exist in water. There are stronger bases, but these are not stable in water. For example, if you put oxide in water, it immediately attacks the water to form hydroxide. And so hydroxide is a base. So hydroxide is what we call amphoteric or amphiphilic. That is, it can go either way. Then we go to water. And I see water here. Water, is it a very good acid? No, it's pretty poor acid. But it can act as an acid, so I'm going to put an A here on water. And then I scroll up the chart and I see water up here. Is it a very good base? No. So it's not a very good acid nor a very good base. So a lot of people ignore it, but you can't always ignore it because sometimes it's the best you have. So even though it's weak, there could be something even weaker. And there are things that are even weaker, right? And so water can be the most reactive species you have present. And so we can't ignore it.
Is it, Professor, because it's a conductor?
Water is not a conductor. Water is an insulator. Pure water. Tap water is a conductor, but tap water is contaminated with electrolytes.
So here we're talking about
The reason we have to worry about water is because water can donate a proton and water can accept a proton. If water donates a proton, we form the conjugate base hydroxide. So if water donates a proton, we form hydroxide. If water accepts a proton, here, if water accepts a proton, that is, water is the base, it accepts a proton, we form the conjugate acid hydronium. And so the reason why we have to worry about water is it can form hydroxide and hydronium in acid-base reactions, Bronsted acid-base reactions.
So only the tap water is one.
I'm sorry?
So only the tap water.
Oh.
And we can say that we use it because it is a conductor.
We're not trying to conduct electricity here. We're just saying what we're trying to do is we have hydrogens we just want to see who can gain a hydrogen, who can lose a hydrogen. That's all we're doing. So it's not related to electrical conductivity. In fact, if we use tap water for this, would be poor technique because we don't know what's in the tap water. And you shouldn't use tap water for this particular reaction. We have to use DI water or distilled water. There's a difference in DI water We don't have distilled water. We don't have distilled water because it's too expensive. That's why we use deionized water. Deionized water removes the ions using these what are called ion exchange resins, which kind of filter out the ions. But still, it's expensive. I think we pay about 60 cents a gallon for the DI water, but the distilled would be more expensive. Although I was at the supermarket and I looked for the gallon of distilled, and it wasn't that expensive. It was $1 something. But you know, it requires energy, a lot more energy, right, to distill. Although the price isn't all that different. So we have three things that can donate protons. Phosphoric acid can donate a proton, or H+, hydroxide can, and water can donate. Sodium ions cannot donate hydrogen. They don't have any hydrogens on them. Okay, but we only have two things that can accept a proton. Phosphoric acid doesn't want another proton. If phosphoric acid gains a proton, it forms H4, PO4 with a positive charge. It's going to be unstable. Sodium ions don't want a proton. What would form was an NaH2+ cation. That's not going to happen. However, hydroxide can accept a proton. If hydroxide accepts a proton, what do we make? Water. And water can accept a proton. If water accepts a proton, what do we make? Hydronium. And so those are okay. And so that's the first step. As we inventory, what was the next step? Determine the strongest acid and the strongest base present. The strongest acid is going to lose its proton easiest. So out of these, let's rank them. We rank them based on the chart over here. And so we're comparing phosphoric acid, hydroxide, and water. So the ranking goes phosphoric acid is at the top, then water, then hydroxide. Uh-huh.
Is the box wrong though? Like indicate that they're the strongest? Is the box?
The box indicates the strongest. This box indicates the strongest acid that can exist in water. These acids up here are too strong to exist in water, so they immediately react with water in a hydrolysis reaction to form hydronium and chloride. This will form hydronium bisulfate, and this will form hydronium and nitrate. And so these ones will react. This is called the leveling effect. These ones are just all too strong and they all level out to here, hydronium. This is the level of the leveling effect. There's a leveling effect for bases too. All the strong bases, stronger than hydroxide, will level to hydroxide because all of these will accept a proton from water. So all these will hydrolyze water to form hydroxide, and that leveling effect is it's complete. Whereas these bases up here only partially hydrolyze water, and so it's not level. They're at different levels because it depends on how strong the base is or how strong the acid is. And so, so the box here is to show the level of the leveling effect. So the strongest acid here is phosphoric acid. And then we do the same thing. Which of these is the strongest base? Yeah, so we start at the top here and then work our way down. So we have hydroxide versus water. Which one do you think is stronger? Do we even need the chart for this one? Hydroxide, for sure, is stronger. So the reaction that we predict is going to be between phosphoric acid and hydroxide. And so we'll just go phosphoric acid plus hydroxide yields what? Yeah, water and dihydrogen phosphate. Okay. If we have extra hydroxide left over, well, actually, let's go to the next step before I get there. The next step is to determine driving force, if any. The driving force is going from a stronger acid to weaker acid, and a stronger base to a weaker base. And so what we have to do is this. This one can only act as a, what? Acid. And so this one is just an acid. However, hydroxide can act as an acid or base. In this reaction, what does it act as? The acid or the base? The base. Now, dihydrogen phosphate can act as either. Dihydrogen phosphate occurs on both sides of the chart. And so in this reaction, what is dihydrogen phosphate? Is it an acid or a base? And the same thing with water. Water is on both sides of the chart, so water can act as an acid or base. What it acts as depends on what you react it with. I don't know if that's going to act as acid or base. It depends on what you react it with. And so in order to figure this out, we look at the reverse reaction here. If we were to go backwards, who loses, who gains? So if we were to go backwards, does dihydrogen phosphate lose, or does dihydrogen phosphate gain a proton? It gains a proton. And so that seals it. If dihydrogen phosphate gains a proton, then that means it must be the base. And then that means water must have lost a proton, and it's the acid. All right, now what we do is we set up a competition. Remember, we want to go to the more stable side, so which way is downhill? Are we going uphill or downhill in this reaction? If we're going downhill in this reaction, then we have driving force. So what we're going to do is we're going to compare the two acids. Of these two acids, phosphoric acid versus water, which one's stronger? Do you even need the chart for this? Which one's a stronger acid, phosphoric or water? Phosphoric. So we're going from stronger to weaker, and that's the driving force. Also, the bases must follow. You know, if the acids are like this, the bases must be like this. It's always got to go strong, strong to weak, weak, or weak, weak to strong, strong. It can never alternate strong, weak. That never happens. It's because of the conjugate relationship. And so we have driving force present for this. This we call step one. Now, if we have extra hydroxide, we could go on to step two, which I'm going to just separate here. Step two would be taking the dihydrogen phosphate and reacting it with another hydroxide, etc. I'm not going to go there. So this is the Bronsted method here. This is also a metathesis reaction, because what we have is we have H3PO4 plus sodium hydroxide. And so it fits the A, B plus C, D pattern. In metathesis, we react to completion. That's typically what we do in metathesis. So what is A? A is H plus. What is B? B is phosphate. C is sodium ions, D is hydroxide. So what we're going to form here is going to be hydrogen ions with hydroxide ions, which is water, and sodium ions with phosphate ions, which is going to be sodium phosphate. So if we take our H3PO4, we're going to need 3 sodium hydroxides, and we're going to form sodium phosphate plus 3 waters. Liquid. Water should be liquid. This would be the CE. The driving force for this is going from stronger acid, phosphoric acid, to weaker acid, water. Driving force. And so when we do metathesis, we'll do a CE, we'll do the IE. The IE, is phosphoric acid strong or weak? It's weak, so we don't ionize it. Is sodium hydroxide a strong electrolyte? Yes, soluble salt. 3 sodium ions plus 3 hydroxide ions. Sodium phosphate, strong electrolyte? Yes, soluble salt. 3 sodium ions plus phosphate ions. Water, strong electrolyte? No, plus 3 waters. And then we do the NIE. The NIE, we get rid of the spectators. Looks like the sodium ions are spectators here. And so it's going to be H3PO4 plus 3 hydroxides yields PO4 3 minus plus 3 waters. That would be the NIE. So metathesis, we react to completion. In Bronsted, if we want to react it to completion, we'd have to do 3 steps. And so step 1, we neutralize the first proton. Step 2, we neutralize the second of the remaining protons. And step 3, we neutralize the last proton. Okay, is that clear for this? Normally we have to check all reaction types. So what's the formula for sodium ions? We know that. What's the formula for monohydrogen phosphate? And what's the charge? So sodium monohydrogen phosphate will be Na2HPO4. Potassium hydrogen sulfate. What's the formula for hydrogen sulfate or bisulfate? HSO4. Charge? Minus. And so that's just KHSO4. This looks like double replacement. A, B, C, D. A is going to be sodium ions. Actually, I already have it written up here. Let's just use this. This is my A. My B is, my B. Should I knock off that hydrogen off B? Or should I leave that hydrogen on it? Is B phosphate or is B monohydrogen phosphate? Yeah. The only reason I'd knock off that hydrogen is if B were a strong acid. Is HPO4 2 minus a strong acid? No. And if it's not a strong acid, you leave the hydrogen on there. But why did I take the hydrogen off in the previous example here? The reason I took the hydrogen off is because it's not water that's taking the hydrogens off the phosphoric acid. It's the hydroxide. And when I compare the strength of water versus hydroxide, hydroxide is much more effective at taking hydrogen ions off than water. And so we leave H3PO4 as is because that's what we find the major species in water, and then hydroxide can attack it. So here we have the H3PO4. Water's not pulling them off, but hydroxide's pulling them off. So that's why I left it on up there. So this looks like a metathesis, doesn't it? And so if I do the metathesis, I'm going to form potassium monohydrogen phosphate and sodium bisulfate. It doesn't matter if you swap the AC or swap the cations or swap the anions. We're just looking for a good combination, so it doesn't matter which one you swap. But first thing is we got to look for driving force. Do either of these precipitate? No precipitate. Do either of these decompose into a gas? No gas. What's the last thing we look at? Stronger acid to weaker acid? Yes? No. No. So no driving force. And so what we say is that there's NR. NR means no reaction. However, there is a reaction. It's just not metathesis. So what we should say is no reaction for metathesis. And so what is the reaction that occurs here? Well, if it's not metathesis, then we should consider redox, and we should consider, what are the three types of chemical reactions? Acid base. So let me tell you, there's no redox. We'll look at redox later today. But why don't you see what the acid base reaction is here? What am I missing in the inventory up here? Water. You can't forget water in all of these. Let me go on here. Let's see, we're going to go through here. We're just going to look at Bronsted. We're going to do this other stuff later. And so what I'm going to do here is go to redox reactions next. So for redox reactions, we have a number of different ones. Actually, I should put in one more here. Approaches. Numbering got screwed up here. I'll put that here. We already did element plus element to an extent. So, but these are the approaches that we'll take to these. What we have here, an element plus element. The elements on the left side of the periodic table tend to lose electrons. The elements on the right side of the periodic table tend to gain electrons. And we can figure out how many they lose and how many they gain by their preferred charge or charges. Then we have single replacement, but single replacement can be a trap at times. There are a lot of exceptions to single replacement. And so rather than using single replacement, I use a chart. The advantage of using single replacement is if you know what the traps are, if you know the exceptions, then it's fast. Then we have combustion reactions. Combustion, and then there are more advanced methods. Chart method, potential diagrams. Finally, the skeleton redox. We're not really going to do potential diagrams. And so we're going to look at these methods in bold. And this is going to be the most important method here, the chart method. I'm going to look at. And so let me talk briefly about the other ones first. So element plus element, let's say I have carbon plus oxygen, two elements. What forms? It might be carbon monoxide or carbon dioxide. If we do complete, normally we do complete. And if we do complete, then we just say carbon dioxide. That is complete, what we call oxidation. Let's go with nitrogen and oxygen. This is more complex. We might form nitrous oxide, we might form nitric oxide, we might form nitrogen dioxide, etc. If we do complete oxidation, what does it form? Complete. What's the highest positive charge for nitrogen? +5. So if we have nitrogen in a +5, I'm not going to write +5 here because having a nitrogen +5 cation is too unstable. And then oxygen likes to be -2. So what we're going to get is, there's a trick for this, figuring this out. It'll be N2O5. That will be complete. We can't go any farther than that. However, if we take aluminum and oxygen, then we pretty much only have one choice, right? Aluminum is going to lose 3, and oxygen is going to gain 2, and then we're going to form Al2O3, which is a solid. These are examples of element plus element combination reactions, where we could get a mix of products or we could get just one. Let's try this one. Let's try magnesium plus sulfur. What do you expect to form? Magnesium sulfide, MgS. So, one more. Iron plus oxygen. Yeah, we might form iron 2 oxide, FeO, and or Fe2O3. If we do complete oxidation of our iron, we form Fe2O3. These are not balanced. And so typically, to avoid this confusion, we're just going to do complete oxidation. However, like nitrogen doesn't like complete. Nitrogen likes to form NO, maybe NO2. Yeah. N2O5, it doesn't go that far. Iron likes to go all the way to rust, Fe2O3. These ones only form 1, so we don't have to worry about it.
How are we supposed to predict them from combinations of other elements?
Which ones?
Big combinations of other elements. How are we supposed to predict?
You base it on the charge, the preferred charge or charges. And so you predict, give me 2 other atoms you want to predict. What do you want to predict? Gallium and oxygen. So gallium and oxygen, which one do you think wants electrons more, oxygen or gallium? Oxygen. So oxygen is going to get its preferred charge at -2. But gallium has multiple charges. What are the charges on gallium? Gallium goes all the way to plus +3. But gallium's like aluminum, so what we do is we just go G gallium 2O3. Yeah. Keep gallium at +3. It's in group 3. That's probably the easiest. Does that make sense? Just look at its charge. Sometimes we'll get it wrong. Sometimes maybe we'll predict NO or NO2 or N2O5 and what forms is N2O. You know. Sometimes we think we're burning it completely, but we get carbon monoxide formation. We don't want carbon monoxide formation, but sometimes that happens. You know, it depends on the conditions of the reaction. So what we do to simplify things is we say it's complete all the way. You know, like complete combustion, so that there's no carbon monoxide formation. Single replacement follows the A plus BX pattern. A plus BX yields AX plus B. But this is sometimes wrong. The problem is sometimes it's wrong. So we try to force, this is like sometimes you try to force a round peg, or no, let's go with a square peg in a round hole or something like that, you know. You're trying to force it to fit this pattern, but it doesn't fit this pattern. So sometimes it's wrong, most of the time it's right. Well, most depends on what kinds of chemicals you work with. All right, combustion we already talked about, you know. Combustion, we have a CH or CHO. This yields, when we burn it in O2, yields CO2 plus water. Here we're assuming that it's complete combustion, right? Complete CO2. We could have a CHS. A CHS will yield CO2 plus SO2 plus H2O. But was the sulfur completely combusted in this? No, because in order for sulfur to be completely combusted, it would have to go to plus what? Sulfur, the max positive is what? Plus 6. Here it's only plus 4, but here's where it stops. You know, under these conditions, we only get SO2. We don't get SO3, which would be complete. CO2's been completely combusted. But these are things that are descriptive chemistry that people just see what happens. You know, it's hard to predict theoretically sometimes. You know. So this is the standard combustion you should know. What if we have a CHN? N is a mess. CO2, yes. H2O, yes. But N, we form a whole bunch of different ones. NO, NO2, etc. So it usually comes out as like a mixture of oxides of nitrogen. So we just call it NOx, NOx. You can tailor the conditions to always get a certain oxide, you know, but it's a bit messier. And therefore, the NOx are processed using catalysis to, we call it reduce it back down to nitrogen. And so we're going to focus our time on the chart method. Let's take a look at the chart method here. This is the redox chart. It's the chart to the left over there. Except that one's upside down compared to this one, but it doesn't matter. Upside down, right side up, it doesn't matter. It still ranks things. And so in the redox method, we do the same step as acid base. We inventory the species. And then we find the strongest oxidizer present, find the strongest reducer present using this chart. This chart is in chapter 20 of your book, or Appendix D. Appendix D is a much longer chart. It's the same thing. And this chart ranks what we call the oxidizers on the left. The oxidizers take electrons, and all these reactions take electrons, but they take different amounts of electrons. For example, 2 electrons, 2 electrons, 2 electrons, 5 electrons, 6 electrons, 4 electrons, etc. So they take different amounts of electrons depending on what they want to do. And so the oxidizers like electrons. These species are electron poor, so the best oxidizer is the most electron poor species. The most electron poor species on this chart doesn't look like it should be, but it is. It's fluorine. Fluorine wants 2 electrons to make 2 fluorides. Ozone's electron poor. Ozone takes electrons to form oxygen. This one's like electron poor. This is like a disulfate ion, but it's not called disulfate. It's called something else. And disulfate usually lose 1 oxygen. This is a peroxide. This is also peroxide. These 2 are peroxides. Permanganate already, if you look at disulfate, or not disulfate, but it's a per-sulfate. If you look at that, there's a 2- charge. So why is this electron poor? It's electron poor not because of this. It's electron poor because of either the sulfur or the oxygen. This permanganate has a negative charge. The permanganate's electron poor because of manganese. Manganese is +7 here. So +7 manganese is maxed out. It's electron poor. This is lead-4 oxide. Chlorine wants electrons. All these species want electrons. People have asked me, do I need to memorize this chart? No, you don't have to memorize the chart, but there are certain patterns in the chart that you should have memorized, so that if something doesn't occur in the chart, you can kind of estimate how it's going to react. Does that make sense? This chart is not comprehensive. The chart in Appendix D is much more comprehensive, but that chart isn't comprehensive either. There's lots of species that don't occur on the chart, but you can have an idea of how they're going to behave in redox reactions based on some of the patterns that you see here. Okay. So all we do is we inventory and see if any of those species occur on the chart here, and then rank them. Then what we do is we combine the strongest oxidizer, half reaction. The reactions written there are half reactions with the strongest reducer, making sure that the number of electrons cancel, and we also have to flip one of those. Not everything can be an oxidizer, so we don't take an oxidizer plus an oxidizer. We take an oxidizer plus a reducer. So when we use a reducer, the reducers occur on the right side of the chart, but we need to make it a reactant. And so in order to make a reducer and a reactant like iodide, if iodide is a reactant, what we have to do is we have to flip this equation. So it goes iodide forms iodine plus 2 electrons. And so what we have is we have one species take electrons, the other species gives up electrons. We have to have that. And so both can't be oxidizers and both can't be reducers. So one takes electrons, the other gives up electrons. The one caveat we have to worry about here is that the number of electrons taken must equal the number of electrons given. And so in other words, the electrons have to balance. And sometimes that's difficult because sometimes one oxidizer wants 5, but the reducer only gives up 2. And so we have to come up with a common number of electrons. In other words, we have to come up with a common factor. We'll talk about that later. And that we do by changing the coefficients. Then we simplify it, and then we look for a driving force. The driving force is stronger oxidizer to weaker oxidizer, stronger reducer to weaker reducer. And this method only yields NIE, just like the last Bronsted acid base only yields NIE. And so we'll do this one first. This one, if you did this one using single replacement, you get the wrong answer. Well, you sort of get the wrong answer. So let's talk about copper and nitric acid. This looks like single replacement to me, A plus BX. If it's A plus BX, then I'm going to get AX plus B. AX is going to be copper with nitrate. Now I have two choices. I could go copper 1 nitrate or I could go copper 2 nitrate. Which one should I do? Copper 1 nitrate or copper 2 nitrate? And this comes from observations. Copper 2 nitrate is much more common. And copper 2 is more preferred. And then B is hydrogen, but hydrogen likes to be diatomic. Then we use the activity series to predict, and we see that we want to go from more active to less active. And when we look at this, this is less active, copper, and this is more active. We don't even need the activity series for this. What would you, let's say you're driving and you have a tank full of copper pennies versus a tank full of hydrogen gas in your trunk. Which one do you think is more stable? Having a bag full of pennies or having a tank of hydrogen gas in your trunk? Not weight. We'll ignore the weight. Safety. Safety-wise. We'll keep the weight the same. 10 grams of copper or 10 grams of hydrogen gas stuffed in your trunk. Which one would you feel safer driving? Yeah, copper is more safe. I mean, the 10 grams of copper is like 5, 6, 7 pennies. 10 grams of hydrogen would cause an explosion. Copper is more safe. So that's less active. This is more active. Therefore, there's no reaction. But we can't say no reaction. This is no reaction for single replacement. There is a reaction here, and it's not single replacement. Do you know what the reaction is? But redox does occur. So you can use single replacement, but you have to remember that nitric is not a normal acid. Nitric is what we call an oxidizing acid. Oxidizing acids do not work in single replacement reactions. And so if I made this hydrochloric acid, I'm good. So in Chem 4, the instructor would never put nitric acid there because they know you'd get the wrong answer, right? And so in Chem 4, we wouldn't use nitric because that's oxidizing acid. You don't put oxidizing acids into a single replacement reaction. It won't work. It's like trying to put the square peg into the round hole. It just doesn't work. So there are four big exceptions. You can memorize the 4 big exceptions to single replacement and then just use single replacement. And if you encounter one of those exceptions, then you have to use an alternate method. Here, oxidizing acid, do you know all the oxidizing acids? Well, first thing is you'd either have to memorize all the oxidizing acids or you have to figure out what are the oxidizing acids. And not all the oxidizing acids occur on the chart there, but you can figure them out knowing the pattern, right? This is one of the patterns I talked about. Number 1, memorize or know how to figure out what the oxidizing acids are. That's the exception. Exception number 2 is when we're dealing with elements that are halogens. Halogens are like chlorine, bromine, iodine. This method fails. This method fails, so in like Chem 4 and Intro Chem, they give 2 single replacement patterns. One single replacement pattern for halogens, another for non-halogen elements. Exception 3 is when you have very reactive elements like sodium and lithium. Exception 4 is when water reacts. So I'm not going to go through. I don't want to. I mean, I don't want to overwhelm you with too much memorization. So rather than doing the memorization, we could use the chart method. The chart method, we don't have to memorize all those exceptions. And so we'll just use the chart method here. The chart method is inventory. So we have copper, we have H+, we have nitrate, and we have one other thing. What's the one other thing? Water. And then we go to the chart. When we look at the chart, does it occur on the left side of the chart or the right side of the chart? And so where is my chart? Is here. We look for copper, and I see it here. It's on the right side of the chart. I don't see it on the left side of the chart. The only thing on the left side is copper 2 ions. And copper metal is not the same as copper 2. There's no copper metal or solid copper on there. And so it's on the right side of this chart. It's on the left side of that chart. The left side of that chart are the reducers. The right side of the oxidizers. The left side of this chart are the oxidizers. The right side of the reducers. So it depends on what chart you use. And therefore, we need an anchor system. We need to memorize something because it doesn't matter which chart you use, but you have to know which one's the oxidizers, which one's the reducers. So you should memorize the strongest oxidizer on this chart. Do you know what the strongest oxidizer on this chart is? Fluorine. So you have to memorize fluorine is the strongest oxidizer. So fluorine occurs at the top left of this chart. Do you know where fluorine occurs on that chart? At the bottom right. So it doesn't matter. Okay, bottom right's the strongest oxidizer. And so this is like being out in space. You know, what's right side up, what's upside down. It doesn't matter as long as you know. You know, if you flip yourself upside down, then that chart looks perfectly fine, right? Okay, and then the strongest oxidizer is fluorine, F2. What is the strongest reducer on the chart? Lithium. Lithium metal is the strongest reducer, so you need that as a reference point. F2 and Li solid are the two. So what we do is we consult the chart here, and we look for it. And so I see copper. Copper is what I'm going to call an Ra, reducing agent. And then I see H+. H+ only occurs on the left side of the chart, so that's an OA. And then I see nitrate. Nitrate occurs on the left side of the chart. That's an OA, but nitrate needs something. And so when we go back to the chart, it's not nitrate alone. Nitrate needs one other species for it to react. So H+ doesn't need anything. You see H+ is here. It's in purple. There's a reason it's in purple. I'll talk about that much later. But when we look at nitrate, you see nitrate here? What does it need? It needs H+. And so we call that acid. Nitrate needs to be an acid, like nitric acid. Except nitric acid is HNO3. We need excess acid here. For every nitrate ion, we need 4 acid hydrogens. So if I had 4 HNO3s, 3 of the nitrates would be spectators. Or I could just have sodium nitrate and add acid to it. That's fine. But I have H+ present. And so this is an oxidizer here if I have H+ and NO3 together. And this is an oxidizer alone here. And then water. We'll take a look at water. Water, this chart is weird because water is here at the bottom. Do you see that? Water is here at the bottom, but it's not the bottom. When I look at the minus 0.828, minus 0.828 positions water between these two. And so water is actually between zinc ions and aluminum ions. And so water is not the worst oxidizer. It's positioned there. And so water is, it's a pretty poor oxidizer, but it still can potentially react. And then we have water up here. I have water here, and I have water here. All the other waters need something else. So for example, this water needs O2, so I can't use that. So which of these two waters should I use? Which of those two waters should I use in my ranking is I should use the stronger of the two waters. Which one is the stronger of the two waters? The one that's closest to the strongest. The strongest species on the right side of this chart is lithium. Lithium's at the bottom here. And so the stronger of the two is this water. But how can these two waters be stronger than those two? Aren't they just water? Yeah, they're water, but they form different products. So this water, when we go backwards, forms oxygen. This water, when we go backwards, forms hydrogen peroxide. Well, hydrogen peroxide itself is very reactive. Oxygen is much more stable, so this water is better. And so water is like, there's not a fancy word for this, like there was for acids and bases. Water can go either way, and so it can act both as a oxidizing agent and a reducing agent. And then we pick the strongest. The strongest reducing agent, it turns out, is copper. Because even though we ranked water here, this water of the two are stronger. It's still weaker than copper, which is here. And copper is a lot weaker than lithium, which is here at the top of the chart, which is the bottom of this particular chart. It would be the top of that chart there. Okay, so out of our two reducing agents, copper is the stronger. Now we have three oxidizing agents, nitrate and H+ versus H+ versus water. So when we compare it, let's see, the strongest is fluorine, so we'll work our way down. Fluorine, the first one we hit is nitrate and H+. The second one we hit is H+ alone. And the last one we hit is water, which sits between zinc and aluminum ions. And so the strongest, did I record this? Yeah. The strongest oxidizer is going to be over here. And then what I do is I copy the equations from the board. Except this one I have to reverse. So I go copper solid goes to copper 2+ plus 2 electrons. And so I reverse this one. And this one I just write down as is. As is. And so this one is NO3- plus 4H+. I'm just going to copy it straight from the chart. Plus 3 electrons yields NO plus H2O. 2 H2Os, sorry. It's 2 H2O liquids. And then I combine these, but the electrons are mismatched. So can you combine these for me?
Yes, just gotta use an alpha electron.
Yeah, so you have to multiply. This is regarding the exam I want to talk about. I have the multiple choice. I just didn't. I need to factor in the partial credit on the multiple choice for the multiple answer ones. But I'll hand these back to you. And then for the test, maybe this is what I'm decided to do for the test. The nomenclature part was worth 7 points. And so what I'm going to do is I'm going to give you a chance to recoup some of the points or maybe earn some bonus. And so next week I'm going to retest you on the multiple choice here. And it's going to be worth 3.5 bonus points. So like 50%. Okay. So you can recoup some. If let's say you got them all correct, then that would just be all bonus.